We said that exponential functions are one-to-one, which means they have an inverse function. And we're now ready to talk about what that inverse looks like. So let's start by talking about the exponential function 10 to the x, and we're just going to plug some different values for x into this. So when x is 0, 10 to the 0, well, anything to the 0, is 1. 10 raised to the first power is 10. 10 squared is 100. 10 to the third is 1,000. And 10 to the fourth is 10,000. So now, based on what we talked about with inverse functions and how inverses switch the x and y coordinates, this means that the inverse of this function would have to map 1 to 0, 10 to 1, 100 to 2, 1,000 to 3, and 10,000 to 4. So we define this function, the function that takes 1 to 0, 10 to 1, and so on, as the log of x, or occasionally you might see it written as the log base 10 of x, but if there's no number there as a subscript between the log and the x, assume that it's a 10. And this is what we call the common logarithm function. So the way that this function is defined, the log of x is equal to some number k if and only if 10 to the k is equal to x. So that's how a logarithm is defined in terms of an exponential function. Now this is specifically for the common log function whenever we have a base of 10. But we can generalize this idea for any base. So if we're working with the exponential function a to the x, then the inverse of that function is going to be the log base a of x. And the way that that is defined, the log base a of x is equal to k if and only if a raised to the k is equal to x. And specifically, if the base a is this special number e that we've talked about, then the inverse becomes the log base e of x, which we have a special name for that, the ln of x, which is what we call the natural log function. So just remember, if you see log of x with no number there, it's understood to be base 10. If you see ln of x, that's understood to be base e. So what we want to do with these first few examples is just to get used to this definition and switch back and forth between log notation and exponential notation. So if we're given the equation log base 3 of 4x is equal to 5, we're comparing this to what we have here to rewrite it so that it looks like an exponential equation. So comparing these two things, you see that the 3 is in place of the a, the 4x is in place of this x, and the 5 is in place of the k. So when we put all those things in their appropriate place in this expression, we end up with 3 to the 5 is equal to 4x. Log of 1,000 is equal to y. Now remember, since there's no subscript here, this is understood to be base 10. So comparing this to our definition, 10 is in place of the base a, the 1,000 is in place of the x, and the y is in place of the k. So when we rearrange it as an exponential equation, it's going to look like 10 to the y is equal to 1,000. And now we're going the opposite direction. We're given an exponential equation, and we want to rewrite it as a log equation. So comparing this with this, the 3 is in place of the a, so that's our base. The 2x, that's the exponent, so it's in place of the k. And then the 5, the number on the other side of the equal sign by itself, that's in place of the x. So when we put those in place of the a, x, and k here, we will have the log base 3 of 5 is equal to 2x. And then comparing this to this, e is in place of the a, the 7 is in place of the k, and b is in place of the x. So when we rearrange it in log form, it's going to look like the log base e of b is equal to 7. But then remember, log base e is the same as natural log. So we can rewrite this as the natural log of b is equal to 7.